So hello everyone, my name is Styliani Douka. I'm in the same team as the people that presented before today, and I'm going to talk about my work about growing arbitrary DAG neural networks. We will explain in the next few slides what this means. And also before we begin, I would like to thank the organizers for inviting us here to present this work, and also all of you for being here today. So first of all, I will do a little introduction of what exactly it means to have a DAG neural network. I will remind everyone a little bit the methodology of what we saw this morning, because we have also been on a lunch break and we might need a refresher. And I will talk about strategies, about how we can choose where to add new layers, where to add new neurons, and so on. There had been a lot of questions before about how we choose which layer to grow. So we dive a little bit more on the details of the strategies here, and then we will conclude our presentation. First of all, before we had seen how to train and grow neural networks simultaneously, when we have a concrete structure, so we have 2 hidden states, we have 3 hidden states, 3 or 4 layers in a network, and we add neurons to existing layers. In this talk, we will talk about how we can add completely new layers in a constraint-free manner. So we can end up with neural networks that look like this. So in this structure here, this is an example of a type of directed acyclic graph neural network that we can get with our method. And here, every directed edge is a linear layer, which means that this is where our parameters are stored, and this is where the multiplications with the input happen. And all the nodes are hidden states. These are intermediate representations of data where we connect multiple outputs. So this is the opposite of having a sequential network like we had before. For example, if I have, before we were seeing neural networks that were like this, that had a layer here and then a layer here. And now we can have, for example, a layer here. So we don't have a sequential structure anymore. We can create any network in an arbitrary form. And usually we don't do that, especially in architecture research, because to create these graphs is not trivial, to create them manually. Because in architecture research, we usually have a pool of networks. When we're doing a simple naive approach, we have several networks that we try that are usually sequential networks with 2 hidden layers or 3 hidden layers and so on. And it's not very easy to have this kind of structure and search in all the possibilities of what is the best architecture to use. But when we do it in a growth method, we can create this type of layers because we have the freedom of adding layers wherever we want. This creates, of course, more possibilities of where the new additions can happen. This can be very computationally expensive. So this is a problem that we have to solve with the strategies of how to grow the networks. And the question that arises here is, how do we decide where to add these new layers, because the possibilities increase. So a little reminder, we have here our manifold and tangent space that Guillaume presented before, where we have all the possible functions we can approximate with a fixed architecture. And we have the tangent space, which are the functions we can approximate with small parameter updates, usually with gradient descent. And we define with the desired update the V that we have seen before. We have a desired update about where our parameters want to go in order to have a better outcome. And this usually is outside of the tangent space because our network is not expressive enough and it cannot represent functions that appear here outside of our tangent space. So what we do instead is we take the projection that is the possible updates over the existing parameters of the network. We have seen this before. And this creates a gap here, which we call the expressivity bottleneck. We define it again with V orthogonal. And it is nothing more than the desired update minus the possible update of all the existing parameters of the network. And we define its norm with psi here. Yes?
To the next, because if you have such an irregular one, that might be problematic in technical implementation.
Yes, ideally we would want to have a timer to know when the network is not expressive anymore. For example, if the loss stops decreasing, we can figure out that we have exhausted all these procedures that we can have right now.
So each node must know whether all nodes before it has finished computing.
Yes, technically yes. But for these experiments, we will see that we do it in a fixed time. So we have a specific number of steps that we train the network normally, and then we grow it. These types of networks are a little bit more complicated. So we'll explain here again that the linear layers here are the arrows of the direct acyclic graph. So this is where our parameters appear. And the nodes are the hidden states, so intermediate data representations. And we represent here all the pre-activity, so the data representation before we apply the activation function as alpha, and the post-activities as b after the activation function, or x in case of the input. Let's assume that we want to add a completely new node here that we denote as 1. For this case, we need to add a new layer here for the input, denoted as alpha, and an output layer denoted as omega. So we have 2 new linear layers that we need to calculate their parameters. So the order of operations here is we do only a single forward and backward step, a backward pass, to calculate the expressivity bottleneck in all the pre-activities in the whole network. So we know exactly the expressivity bottleneck in all the nodes that we have in our network. And then we can proceed a little bit differently than the sequential case. Before we had seen that we need to take into account all the existing parameters so that we don't have redundancy in the new neurons. But in this case, the existing parameters also include parallel layers. For example, in our case here, because our output layer outputs to this node here, we also have the existing weights W2 and W3 here that output in the same node. So these are also existing parameters. So in our case, the expressivity bottleneck is the desired update minus the sum of all the possible updates that we can do with these existing parameters. Because in this position here, the output on the same node, so we need to take them into account so not to introduce redundancy in the network. And another problem that we encounter here is that we cannot ignore the nonlinearity anymore because in the simple case, we could increase the size of a neural network, and we had seen that we can ignore the activation function, but this is not the case here anymore. So in order to calculate these new weights, alpha and omega, we need to use gradient descent. We cannot use an exact solution anymore like SVD. So we need to solve this function here, so to minimize the output of these neurons with respect to the bottleneck we calculated in this position. And you see here that the nonlinearity still appears, so we solve this with gradient descent in order to find the best alpha and omega for the new layers to add here. So these are the 2 key differences that we experience when we create networks like this. But after this, we can solve this as before. And in this case, to add a completely new node, it's exactly the same as increasing the size of an existing node, because we assume that the alpha would be here, for example, and the omega would be here, and still we have existing parameters that we need to take into account. So everything else stays the same. So in order to pass into the experiments, there is a little technical detail. We have a trained data set that we use to calculate the expressivity bottleneck, the alpha and omega parameters, the amplitude factor that Manon mentioned before, and also to do the intermediate training in between the growth steps. And we have another split of the data set, which is the development, that we use in order to choose exactly where to add the new neurons, the new layers, and so on. This is the loss criterion that we use for greedy selection based on the loss. We will talk more about the strategies in the next part. So here we have results of growing a direct acyclic graph network on the MNIST dataset, which is the handwritten digits, that was run for 7 GPU hours, which for architecture search at the same time as training is quite low, to do this only in 7 GPU hours. And we see here in the zoomed part the accuracy of the trained dataset, with respect to the accuracy of the development dataset. So this one is used to train the network, and this one is used to choose the best expansion. And we see that for as long as we train, we have a kind of overfit on the trained dataset, which means that the parameters of the network imitate the given dataset too well, so it cannot generalize to a different dataset like this one. But in the moment that we increase the size of the network with a new layer, we see that these two accuracies match, and we have a better generalization between these two datasets. So it's like we escape local minimum of the current architecture, and we can move forward and reach higher and higher accuracies in the training and validation. And we can also see with green the actual test dataset that increases slowly, but we see the increase up to around 96%. And on the other axis, we have the number of parameters that we see every 500 steps, they increase. So this is a fixed schedule that we use. Every 500 steps, we increase the size of the network here. And then the problem that we have because of the MNIST dataset is not a lot of people do architecture search on MNIST because it's quite a simple dataset. So we had to use historical results from Jan LeCun. And here we see the test accuracy in terms of the number of parameters. And with the blue stars here, we have our method by growing a DAG network. And we see as the number of parameters increases, so does the test accuracy, up to a bit more than 96%. And we see here by these triangles here, the historical results that present two-layer neural networks. So we have a simple situation like this, where in each case we have 300 hidden states or 1,000 hidden states. So the number of neurons in those are either 300 or 1,000. And we see that with the same accuracy, we have much more number of parameters. So we are doing much better than the historical results. And also these two are using data augmentation techniques like distortions, which means that they have more data to work with. If we remove this, so that we are more fair in terms of our method, then we have even lower test accuracy with much more number of parameters. And of course, we have results from the North growth method that Manon mentioned that has higher test accuracy, but also higher number of parameters. Now here, we could have trained our method more to reach this accuracy, but at this point, the increase in test accuracy was low, was very slow. So we decided not to further train it because the trade-off between complexity and the energy it would take was not worth the effort, so we decided to stay there. So now we have figured out how to add new layers, but we still haven't figured out where to add these new layers. We haven't talked about the strategies. So when it comes to a network like this, we have a lot of options in order to grow it. For example, if we assume that this is a part of a DAG neural network and we want to evaluate all possible extensions that this can do, we have something that looks like this. Now, these are all possibilities that we have to test. We have to evaluate the information bottleneck just once, but all of those are alpha and omega layers that we need to calculate, plus the amplitude factor to see how much they will impact the final loss. And as you can understand, this is highly computationally expensive, and this takes a lot of time to do. So what we want to do is to reduce this action space, this search space, as much as possible. And what we have opted for so far is to find the position in the DAG where the expressivity bottleneck is the maximum, because we believe this is the position where the DAG will benefit more from having an extension of its parameters. So if we assume that this position here is in node 2, then we are working with something like this. So we have much less options to test in order to find where the best extension is. So this is the first strategy that we tried in order to reduce the action space. And also we wanted a different loss criterion that takes into account the trade-off between complexity and efficiency. So we tested the Bayesian information criterion so that we don't have a major increase in number of parameters with a very small decrease in loss, because this would not be worth the effort. So in order to test these strategies, we wanted a general test case. So we created a teacher-student framework where we have a fixed architecture of a teacher that can be 2 layers, 3 layers, and so on. And we initialize its parameters randomly here. What we want to do is to grow the DAG in order to imitate this teacher. So we have random parameters that do not mean anything for us, but they imitate a task that we might need to solve. And we want to grow the DAG to imitate the output of the teacher. So in the first graph here, we have the loss in terms of the epochs that we train for. And this is trained for 6 growth steps. So we do intermediate training for 100 steps, then we grow the network. And we have with blue here, when we use the whole action space, so the experiment that we saw before in NIST, we evaluate our possible actions without doing anything. We have a decrease in the loss that is quite nice. But what we also notice is that when we reduce the action space with the orange here, we don't lose anything in terms of performance. We reach approximately the same loss. So reducing the action space in terms with the position of the maximum bottleneck works quite nice. And this is also much faster because we don't have to evaluate as many actions. And also when we use the BAC criterion, instead of only using the loss, we have a little bit of loss in performance, but this is to be expected with because sometimes the BAC chooses networks with lower number of parameters that have a higher loss. So this makes sense. And now, in terms of cumulative energy consumption that we calculated in our GPU while these experiments are running for the 6 growth steps, we have here the estimated energy consumption for the total process, and we have splits about how long it took to do the intermediate training and also to search for the best action because these two scale differently. And we see here that when we test the whole action space, we have a major energy consumption in our GPU. And when we use the restricted one, it's much lower. But what was surprising here is that the BAC does not lower this further. It's actually higher in terms of median than not using it. And we believe that this is because the BAC chooses networks that have much more possibilities for the actions for the next step. And we can also see that in the split for evaluating all the actions, because we see that as the DAG grows in size, so does the action space that we have to evaluate. And this scales exponentially in terms of the energy consumption that we have in the GPU. So when we choose DAG neural networks that have more actions to evaluate from, then it will take exponentially more energy consumed in order to evaluate this. Now, in my personal opinion, I don't know about you, this reduction in action space was quite impressive. It actually reduced the time and the energy consumption a lot, but I believe we can do much better. So what we have thought about is to use proxies in order to evaluate these actions without having to calculate exactly the alpha and omega, and maybe reduce the ones that we have to calculate exactly in order to save more time and energy. And we were thinking about using the mutual information between the pre-activities and the expressivity bottleneck that we have calculated here. Ideally, we would want a metric that not only shows how much mutual information we have between those two, but also how easy it is to calculate it. For example, if we can do this with a linear connection, or if we can do this with an indirect connection here, this would be very useful. Also, mutual information is sometimes hard to calculate, so we're also thinking about the Hilbert-Smith's independence criterion. We could use covariance metrics in order to do this, or we could even use the Gromov-Wasserstein distance, because what's important here is that these two metrics are not in the same metric space, so we cannot directly compare them with distances. So this is a detail that we have to take into account in order to make mistakes here. But this is the overall goal, to reduce the action space as much as possible, because as we saw before, it scales exponentially with the energy consumption. So to sum up, we have an architecture growth that creates neural networks in the form of any directed acyclic graph. We have a fast neural architecture search compared to if we had to evaluate many networks from scratch, which means that we have to train them and then test them. And also the possibilities are much less because we have to handcraft these possibilities. We have a fast architecture growth. Even with the full action space, it was only 7 GPU hours, and with the reduced one, we can do much better. We have smaller finer architecture in terms of the number of parameters, as we saw in the historical results of Jan LeCun. And overall, this is an energy efficient method. And for the future, we want to test this method to how it scales to larger and more complex data sets, because NIST is not very complex. We want to further decrease the action space with the proxy that I mentioned just before. This is very important. We need to acquire a better trade-off loss criterion because the BAC was not efficient enough. We might need to handcraft this loss function ourselves. And last but not least, we need to calculate the energy consumption of popular architecture search techniques because papers do not usually mention these metrics. Personally, do not usually find energy consumption metrics in the recent papers of the state of the art. And we need these calculations in order to compare our method and prove that it's actually more energy efficient than the state of the art. Thank you. And also, before we pass into questions, I would like to show you the example of the network as it grows. And here again, we will see that the directed edges are layers, and the nodes are intermediate representations. And as the node grows in size, it means that it has more neurons. And we see here a working example of what the DAG looked like for training on NIST after all the steps that we performed. And we see that some of the nodes increase in size because we choose to add more neurons to an existing node than adding a new one. Thank you a lot for your attention.